Why do we age? I mean, really, why? It's one of the biggest mysteries of life. We all experience it, but what's the deep biological reason behind it all? Well, for decades, scientists have been trying to crack this code, which led to this incredible scientific duel between two brilliant ideas, two powerful theories trying to explain the inevitable.
So, let's frame the question. Is getting old just a matter of wear and tear? Like an old car that's slowly falling apart? Or is there something more profound going on? Is aging actually a feature that's been actively shaped and molded by the most powerful force in all of biology, natural selection? That is the core question we are going to unpack today.
All right, here's our game plan. We'll start with why aging was such a puzzle in the first place. Then we'll look at the first big answer from a biologist named R.A. Fisher. After that, we'll see how another scientist, William Hamilton, came along and just completely changed the game. We'll put their ideas head-to-head, look at some amazing proof from the lab, and then talk about the incredible legacy this work left behind.
For the longest time, the evolution of aging was a real head-scratcher for biologists. Early thinkers like Peter Medawar, they had the right idea. He was the one who really popularized this concept of a force of natural selection that gets weaker as an organism gets older. And it kind of makes sense, right? Selection is all about surviving and making babies, so anything that happens after your reproductive years just seems less important to evolution. It was a fantastic intuition, but it didn't have the hard math to back it up and become a real solid theory. And that's where our story truly kicks off.
Okay, so the first person to really put some mathematical muscle behind this idea was the legendary geneticist R.A. Fisher. In his huge, groundbreaking book back in 1930, he laid down the first formal foundation for understanding aging, and he did it with a really powerful concept.
Fisher's big idea was something he called reproductive value. You can think of it like an organism's evolutionary stock price. When you're young, you have your entire reproductive life ahead of you, so your value to the future gene pool is super high. But as you get older and you have fewer and fewer offspring left to produce, that value starts to drop. So natural selection has less of an incentive, you could say, to keep your body in perfect shape. It's a really elegant and intuitive way to explain it.
And for more than 30 years, Fisher's idea was pretty much the standard. But then, in 1966, a young, brilliant biologist named William D. Hamilton published a paper. It was barely even noticed at the time, but it would turn out to be a total landmark, completely revolutionizing how we understand aging. So what Hamilton did was just brilliant. He took that vague idea of a force and made it mathematically precise. And he didn't just propose one force. No, he developed two separate, distinct scaling functions. These equations showed exactly how the power of natural selection weakens with age. And, this is the really crucial part, he showed that it weakens at different rates for two totally different things, your ability to survive and your ability to reproduce. Now, this is where it gets really interesting. Look at the difference he found. The force of selection on just surviving, staying alive, it stays at maximum strength right up until you start reproducing. Only then does it begin to drop off. But the force on fertility, your actual ability to have offspring at any given age, that's a different story. That can go up or down much earlier. This separation of survival and fertility was the absolute key insight that Fisher's single-value model had completely missed.
So because you have these two separate forces, both declining but on their own paths, you get this evolutionary space, this window where aging can creep in. As the forces get weaker, bad mutations that only have effects late in life can just build up in the gene pool. Or genes that give you a boost when you're young might have nasty trade-offs later on. Because selection's grip is so weak at older ages, it just can't effectively get rid of these things.
Okay, so now we've got our two contenders. In one corner, we have Fisher's elegant reproductive value. And in the other, we have Hamilton's more complex two-part forces of natural selection. This sets up a real scientific showdown. Let's dig in and see why Hamilton's model turned out to be a much, much better explanation for why we age.
Hamilton himself pointed out the problem with the old model. He was able to come up with these specific scenarios, like imagine a species that actually gets way better at reproducing late in life. In a case like that, his own math correctly predicted that aging would still evolve, but Fisher's reproductive value would actually increase with age, which doesn't make sense. And this proved that Fisher's concept, while intuitive, just wasn't a universal law. And this table just lays it all out perfectly. Let's walk through it. Look at the foundation. Fisher's is based on that nice idea of reproductive value, but Hamilton's is built on a much more fundamental measure of fitness. Under prediction, you see Fisher's model just kind of parallels aging, whereas Hamilton's functions can actually quantitatively predict it. And finally, universality.
That's the knockout punch. Fisher's model breaks down in some cases. Hamilton's is just far more robust and powerful.
But look, the true test of any great scientific theory isn't just about how pretty the math is. It's about whether you can actually test it. And this is where Hamilton's theory really shines. It makes these crystal clear, testable predictions about what should happen if we could somehow manipulate evolution in a lab.
So here's the beautifully simple experimental idea that comes right out of Hamilton's math. Remember how the force of selection on survival stays high until reproduction starts? Well, what if you could just push that start date back? If you force a population to only reproduce at older ages, generation after generation, you should artificially keep that force of selection strong for longer. And that, in turn, should select against aging. And that is exactly what scientists did, using the good old fruit fly. It was so clever. They took one big population, split it in two. For the control group, they just collected eggs from young flies to start the next generation. Business as usual. But for the other group, they threw away all the early eggs and only used eggs laid by much older flies. Then they just repeated this process for dozens of generations, letting experimental evolution do its thing. And the results? It was a stunning, absolute confirmation of Hamilton's theory. As you can see right here on the chart, the flies that were selected for late-life reproduction consistently evolved to have significantly longer lifespans. They had literally postponed aging in the lab. This was direct, powerful proof that the timing of reproduction is what shapes how quickly an organism ages.
The impact of Hamilton's 1966 paper is just huge. It goes so far beyond just explaining why aging starts. It really gives us a complete framework for understanding the entire arc of an organism's life, from the beginning all the way to the end.
So what about the very end of life? Well, here's a totally wild and counterintuitive prediction that just fell right out of Hamilton's equations. His forces of selection don't just decline, they eventually hit zero and just flatline. And this predicts that at very late ages, the rate of aging should stop getting worse. It should level off. We actually see this in nature. They're called mortality plateaus, and Hamilton's theory explains exactly why they exist.
This leads to a really mind-blowing comparison. The scientists behind this analysis argue that Hamilton's forces are to biology what Einstein's theories of relativity are to physics. Think about it. Just as Einstein rescaled our understanding of space and time, Hamilton rescaled how natural selection works across an organism's entire lifespan. It's a fundamentally new way of looking at the universe of evolution.
So, when you put it all together, what Hamilton gave us was this incredible unifying framework. It explains why selection gets weak late in life. It explains why that causes aging to even exist. It explains why aging eventually stops accelerating. And it gives us the theoretical toolkit to actually test and manipulate these processes in the lab. It's the whole shebang, a complete and powerful theory of life history. Which brings us all the way back to our first question. Aging, it turns out, isn't just random wear and tear. As Hamilton proved, it is a feature actively shaped by evolution. And then those amazing fruit fly experiments showed us that its pace isn't set in stone, it's malleable. So if that's true for them, it begs the ultimate question for us, doesn't it? Now that we understand the very forces that have molded our own lifespan, can we, one day, learn how to reshape them?